Good morning, everyone. My name is HyunKyuChoi from Texas A&M University. Today, I'd like to talk about strategies to overcome lignocellulose recalcitrance during 4-phenylsulfonic acid fractionation via kinetic modeling. So let's start with introduction. So due to the growing environmental awareness, chemical industry is shifting toward the bio-based materials. For example, when you take a look at the figure 1, the global biofuel production volume is constantly growing since 2000. This represents the paradigm shift from petrochemical feedstocks to renewable and sustainable materials. And this biorefinery concept, which is the conversion of biomass into fuel, is first proposed in 1980s. However, it has not been widely commercialized due to several challenges, such as feedstock variation, sustainability, and cost variables, such as enzyme cost and chemical cost. Now let's look more in detail the biorefinery process. First of all, as a raw material of bioconversion, lignocellulose is the most abundant and the cheapest material in the world. And it consists of three main fractions, which are cellulose, hemicellulose, and lignin. As you can see from the figure 2, the cellulose serve as a main frame of this lignocellulose, and lignin and hemicellulose bind the cellulose fiber all together and serve as a glue. The fractionation is about separating this biomass into the individual building blocks, which are the cellulose and hemicellulose and lignin. This fractionation is part of the pretreatment, which has been developed to overcome many barriers. For example, there are natural barriers due to the biomass recalcitrance, such as rigid structure barrier and complicated chemical composition. And also, there are technical barriers which hinders the conversion of bioconversion. And also there are cost variable barriers for the economic feasibility, which is about the energy and solvent consumption. In the previous paradigms, the other than the cellulose was underutilized. For example, a biomass was treated and then only the cellulose is obtained and the rest components are disposed of. Only the cellulose go through the further processes such as hydrolysis, fermentation, and produces the biofuel. However, utilizing only the cellulose has not been economically viable. In other words, the economic cost of the biorefinery exceeds the economic benefits. Accordingly, the use of the previously disposed components, which are the hemicellulose and lignin, are pulling attention at this time. It is because the hemicellulose can turn into sugar alcohol and forms the platform chemicals, and the lignin, by the depolymerization of lignin, an aromatic compound which has a high value can be recovered. Likewise, this fractionation sounds very favorable and advantageous. However, it also poses a major challenge to the biorefinery because of their different chemical functionalities. For example, the high crystallinity of cellulose makes it difficult to further decompose it into monomers, and cross-linking phenolic units of lignin makes it difficult to be separated from other building blocks. Accordingly, and moreover, the long and energy-intensive reactions are required when the fractionation has not been performed well. For example, when there are a large amount of residual lignins on the pulp, then half to 2 hours of the hydrothermal hydrolysis and 24 to 70 hours for enzymatic hydrolysis are required for the further processes. And also, strong reagents such as sodium hydroxide and sodium sulfide are needed for the further subsequent processes. Likewise, the conventional fractionation process has limitations, which results in unwanted modification of non-cellulose fractions, and this kind of unwanted modification devalue the potential co-products derived from hemicellulose and lignin. And also, due to the use of strong reagents, it also produces a large amount of effluent, which requires expensive waste treatment to reduce the environmental load. Last and foremost, the fractionation process has not been developed systematically. In other words, modeling and optimization techniques has not been widely applied on the fractionation process, and nobody knows for sure what amount of and what type of solvent works the best for the certain lignocellulose type. So from this point, the modeling and optimization techniques can improve the economy of the biorefinery. For example, from the experiment, a kinetic model can be developed using the estimated parameters. And then using this model, the process can be optimized, which can improve the selectivity and purity of the products, and ultimately gives the better profit Likewise, the cost and revenue can be estimated and optimized by implementing advanced modeling and optimization techniques, which improve the product purity and save the energy consumption, raw material cost, and waste treatment expenses. So this is the motivation of our research, and we designed an experiment and developed a kinetic model and estimate parameters for the process optimization. So let's move on to the methodology section. As a part of experiment, to set up the experiment, the aspen wood chip is chosen and used for the fractionation under the 4-phenolsulfonic acid, aka PSA. And then air-dried aspen wood chips are supplied by State University, New York, and wood chips with 3 different thicknesses, which are the 0.8, 3.0, and 5.0 millimeter, are prepared to analyze the effect of the thickness of biomass. And then the 85 weight% of PSA solution is first purchased from TCI America, and then diluted to make 72 weight% in the reaction vial. Then the reaction vial is incubated in the oil bath at 3 different fixed temperatures, which are 70 and 80, 90 degrees Celsius, to formulate isothermal reactions. And then the soaked and wood chip, aspen wood chips, were manually disintegrated with glass stirring rod, and the jelly-like pulps are obtained and went through the measurement. And from this treated biomass, chemical composition is measured. Specifically, carbohydrate and lignin content before and after pretreatment are measured following the National Renewable Energy Lab standard protocol. The residual sugars in the treated biomass are analyzed using HPLC with a refractive index detector, and the UV ultraviolet viscosity spectrometer is employed to measure the residual lignin in the biomass, where the acid soluble lignin is measured with the absorbance at 240 nanometer wavelength. And in this experiment, the biomass size, thickness, and cooking temperature and cooking time are chosen as independent variables. So after the acid fractionation under different conditions, the properties of the pre-treated biomass are measured. To sum up the operating conditions, 3 different thicknesses of the biomass, which are 0.8, 3.5, 3.0, 5.0 millimeter, and 3 different cooking temperature, fixed temperature, which are 70, 80, and 90 degrees Celsius, and 3 different cooking time, which are 10, 20, 30 minutes, are performed under the fixed PSA solution concentration, which is a 72 weight%. And under these 2 different operating conditions, 2 measurements, which are the solid recovery, which represents the pulp yield, and the lignin content in untreated biomass basis, which is defined as the lignin content in pre-treated biomass times the solid recovery, are measured. And then a kinetic model is developed to describe this acid delignification. Specifically, an equation of a first-order reaction is employed for the delignification kinetics, where the lignin condensation is also captured by considering the reverse reaction. The parameters of the model are estimated based on the experimental data, and the effect of the biomass thickness and temperature on the reaction kinetics is analyzed. So in this, as a fourth reaction, the delignification is considered, which is a transformation of solid lignin into the solubilized lignin content. And also, as a reverse reaction, the transformation of liquid phase lignin into the solid phase lignin is also considered under the first order ordinary differential equation. Then the rate constant, which are the parameters of the model, are estimated with initial gases and experimental data. So first, an objective function is designed to minimize the error dynamics, and the solutions of the deterministic optimization problem are calculated. So in the objective function, it is designed to minimize the deviation between the measured lignin content from the experiment and the model lignin value, while decision variables are the reaction rate constants of the forward and reverse reactions. And this optimization problem is solved using interior point method, which is widely used for the convex optimization problem. The maximum iteration on this optimization is set to be 1,000, and the optimality tolerance is set to 10 to -6, which means that the objective value is lower than this tolerance, the iteration stops and assumed to be converged to the solution. Now let's move on to the result and discussion section. So under different operating conditions, which are 27 different conditions, solid recovery and lignin contents are measured after the fractionation. These experiments are repeated under the identical conditions to calculate the standard deviation, which is given to the error boundary to the model. Under some conditions, the measurements are not available. Specifically, when the biomass size is very big and temperature is very low, the degree of delignification was too low to be detected under these conditions. In other words, the weight difference between the pretreatment and after pretreatment were not detectable on these conditions. So by utilizing the remaining experimental data, the parameters are estimated and the reaction kinetics is predicted. You can see from the three different conditions, like under different conditions, 70 and 80 and 90 Celsius, the predicted model captured the reaction delignification dynamics pretty well, showing the very low root mean square error values. And in this figure, in this graph, as you can see, when the biomass thickness is thinner, the reaction takes faster than the larger size of the wood chip. And this is more clearly shown in the table. When you take a look at the reaction rate constant, first the delignification, the forward direction, it shows the positive relation between the temperature and the reaction. So when the temperature gets higher, the delignification reaction gets faster as well. And also, it's negatively related to the size of biomass. In other words, when the biomass size is thinner, the reaction takes place in the faster manner. Also, when you take a look at the condensation reaction, it shows slightly different tendency. So first, it shows a similar tendency on the temperature. So the condensation also takes place faster when the temperature is high. However, there is an insignificant relation between the temperature and the condensation reaction rate and the biomass size. It might be attributed to the fact that the condensation of lignin is more determined by the dissolved lignin content in the liquid phase, not the biomass size. And this is well summarized in the graph as well. When you take a look at the figure 6, the delignification reaction constants under varying temperature and biomass size, it shows a clear temperature dependence and size dependence. However, in terms of the lignin condensation reaction, it shows a temperature dependence clearly, but there is insignificant and not meaningful relation between the size and the size of the biomass and the condensation reaction rate constants. So to sum up let's sum up the result. First, both delignification and condensations are temperature dependent, and in other words, the high temperature facilitates the both reactions. In addition, acid delignification, the forward direction is dependent on biomass size, and it is due to the high specific surface area of older chips. Small older chips are more favorable of that. The small chips, those are more favorable for the delignification reaction. However, in terms of the condensation, the reverse direction, the biomass size does not significantly affect this lignin condensation. And it might be attributed to the fact that dissolved lignin content would impact in the liquid phase would impact the condensation reaction, not the size, the thickness of the biomass. And as a future direction of this research, first, the behavior of the acid fractionation will be further analyzed by investigating the chemical composition of rest building blocks, which are the cellulose and hemicellulose, and the molecular weight of the components and degree of polymerization. And then the parameters such as reaction rate constants and partial reaction order for each reaction will be estimated, and the effect of the biomass thickness and the temperature and the reaction kinetics will be further analyzed. Then the given mathematical interpretation will be utilized to develop a multi-scale model. And this multi-scale model's goal is to design an optimal fractionation operation while considering the multiple factors that determine the economic viability of bioconversion. So that's all for the content, and thank you so much for the listening. Please feel free to ask any questions. Thank you.